exponential growth and decay. We've looked at many models of things throughout the calculus sequence, which are modeled exponentially. They either grow or decay over time. So in this section, we're going to look at the set of differential equations that model exponential growth and decay. So we're going to start by considering the differential equation dy dt equals y. This differential equation implies that we have a function y that is equal to its derivative. So if we think about the functions we know and the functions we work with, and we think about which one has a derivative that is the same as the function itself, we know one such function. Y equals e to the t. The derivative of e to the t is e to the t. So the derivative is the same as the function. So that particular function is a solution to this differential equation. We could also find the solution to this by doing some algebra. If we bring up the dt, we get dy equals y dt. If we want to bring the y over to be with the dy, we have 1 over y dy equals dt. If we integrate both sides, we get the natural log of the absolute value of y equals t plus c. If we exponentiate both sides, we get y equals e to the t plus c, which is the same as c e to the t algebraically. So we see that not only is e to the t a form that solves this differential equation, but any c e to the t will solve this. Because we know if we take the derivative with a constant in front, that the derivative is the same. Now, if we think about this differential equation, we can talk about how things grow exponentially or how they decay exponentially. This particular form implies that there's a 1 in front of the t. So that's usually the growth rate. We can take this a step further and alter the growth rate while still satisfying our differential equation of this type. So consider now dy dt equals ky. So almost the same as the last, only now we have this k in there. And we know from previous examples that that k tells us that our differential equation has a proportionality constant. What does that mean? This says the derivative is proportional to the size of the population, right? So k is a constant, and we know that if we were to solve dy dt equals ky, if we include what we know from the previous steps, that would equal y equals ce to the kt. So this is our general form of exponential growth and decay. Now, if k is greater than 0, if it's positive, then we represent exponential growth. If k is negative, we represent exponential decay. Now, it's not quite as straightforward as you would think with this because it also is impacted by our c. C is our initial condition. It's the value that we get when t equals 0, because c could be positive or negative. So let's look at some combinations of c's and k's to see how that impacts a general function. So first, let's consider what happens when our growth rate is positive. So if our growth rate is positive, so it's greater than 0, and our c is positive, we end up in the top quadrant, and we can see that our function is increasing over time. We read this from left to right like any other graph, and we can see that our functions go up exponentially for the different positive values of c. Now, if k is positive but c is negative, then that takes our function and turns it into a decreasing exponential function. But you'll see that in both these scenarios, they're getting bigger and bigger, right? So when c is positive, it gets bigger and bigger in the positive direction. And when c is negative, it gets bigger and bigger in the negative direction. Both of these are considered growth because they go off and get bigger and bigger in one direction. So we call this growth. So exponential growth. Now let's see what happens when k is negative. So when k is negative, we see that our function is going to approach 0. Now, the direction it comes from depends on the c. So when c is positive, we start really large in the positive direction, and then we slowly come down until we approach 0. When c is negative, we start really large in the negative direction, but still increase to approach 0. So in both of these cases, our function is getting smaller and smaller in magnitude, and therefore this represents decay. So again, k being less than 0 gives us decay, but how that happens and how that's impacted and where it is all dependent on your value of c. So we might start really positive or really negative depending on c, but either way, our function is going to decay and become smaller and smaller in magnitude. So c and k both impact our function and what it's doing, but growth and decay are dependent on the k value. So let's practice solving some of these equations and make sure we have the general form down to be able to look at these. Example 1. So over here, I'm just going to remind you from up above that if we have dy dt equals ky, then we said the solution is y equals ce to the kt. So how do we know if we have something of this form? So what I want you to notice is that this dy tells us that the dependent variable is y, and that matches the variable that we're talking about on the right-hand side. So if that's the case in your differential equation, you know that the solution is of this form. So let's go ahead and check this out and see how we can set up some of our differential equation solutions. So for a, we have dy dt equals 6y. So we see what's on top. We have dy, and then we see we have a y on the right-hand side. So that means our solution is y equals ce. Now the 6 here is our k. So to the 6t. I know it's t because in the bottom of my differential equation on the left-hand side where I have my derivative, the independent variable is t. So that's what goes up in the power. So this is a general solution because I don't have anything that allows me to solve for c, but I do have my k in this case. Let's try part b. We have dp dt equals negative 0.3p. So again, I'm checking to see if the dependent variable is the one that's on the right, and it is. The top of my differential equation matches. So now I can set up my general solution. So here, because my dependent variable is p, it's going to be p equals ce. Now my k is negative 0.3, and my independent variable is t. It's really important that our variables match the model. We don't want to always use y and t. We want to use whatever is given in the problem. Let's try part C. So here, dq, q is my dependent variable, and it matches on the right. I have 15q. So the solution here will be q equals ce. Now here, I have a k of 15, so 15t because again, it's dt. So in these first three, we notice that we have growth for the first one because my k is positive. We have decay for the second one and growth for the third one. Now let's go on. There's two more parts to this. Part D, we have dz dw equals 5w. So z is my dependent variable here. But notice now that I have a w on the right-hand side. So this is meant just to make sure that you're being careful in checking your differential equations. So this is not exponential growth or decay. This is a differential equation that models something else. So what we need to do is we need to bring the dw up. So we have dz equals 5w dw. And now we're going to integrate both sides. So we get z equals 5w squared over 2 plus c. So we don't have to do any extra algebra because the z is by itself and it's already solved. So this is not exponential growth or decay. Okay, so you have to be really careful when you're solving differential equations that you know if the dependent variable is on the right-hand side, because that is what is allowing us to write this in the form of the exponential. So let's look at E. So we have dz. So z is our dependent variable, and we have z on the right. So we can write it as z equals CE. Now, -4 is our k. And now our independent variable is w. So we have z equals CE to the -4w. Because k is negative, that's going to be exponential decay. So again, it's really important that we use the variables that are represented in the differential equation for our final answer. So these were general solutions. And again, the reason these are general solutions is because we don't have the value of c, which means c could be anything depending on the situation. If we had some sort of initial data, we would be able to solve for c. So let's look at the next example, which does just that. Find the particular solution for each of the following differential equations. We're able to find a particular solution because each of these gives you an initial data point. Part A, dy dt equals 8y. So notice here again that the dependent variable is y, and that the variable we're using on the right is y. So we have a derivative that's equal to some version of the original function. So that allows us to write this in exponential form. So y equals CE to the 8 is our k, t. That's our general solution. Now, if we want our particular solution, we have to use the fact that when t equals 0, y equals 10. So we have 10 equals CE to the 8 times 0. Anything times 0 is 0. So this is 0. And e to the 0 is 1. So what that tells me is that c equals 10. So if c equals 10, then my particular solution is y equals 10e to the 8t. So we find the particular solution that satisfies this differential equation by starting with the general solution and then using the initial information to solve for the exact solution that I want. Let's try part B. dp dt equals -0.25p. So again, my dependent variable is p because that's what's on top. And that matches what's on the right. So I have an exponential solution here. So that means my general solution is P equals CE to the negative 0.25t. And now I can get my particular solution by using my initial data here. So when time equals 0, P equals 135. So 135 equals CE to the negative 0.25 times 0. So we know that the exponent is 0 and e to the 0 is 1. So that tells me that C equals 135. So my particular solution is P equals 135 e to the negative 0.25 t. Let's look at part C. dw dz plus w over 2 equals 0. Notice that this is not in the same form as the problems we had previously been looking at. However, we can bring the term w over 2 over to the right by subtracting it over. So this rewrite will help us put this in a form similar to what we were looking at before. So dw dz equals negative w over 2. So remember, 1 over 2 can be written as 0.5. So we can write this as negative 0.5 w. So by bringing this term over, it's now in the form we've been looking at. Our dw, w is our dependent variable, and that's what's on the right. So we do have exponential decay here, decay because our k is negative. So we have w equals CE to the negative 0.5 z. Notice here that z is our independent variable. So if we want to solve for our specific particular solution, we need to use our initial information. So we have 5 equals CE to the negative 0.5 times 0. So that tells me that C equals 5. So my particular solution is W equals 5e to the negative 0.5 z. So this one had an extra step because it wasn't quite in the same form as the others. Sometimes you have to move a couple things around to realize what form it's in to be able to solve. Let's look at another example. Example 3. Consider a population that's growing at a rate of 5% of the current population each year. If the initial population is given by P naught, or P sub 0, set up and solve a differential equation to model this population. So here, we don't have any variables other than the initial amount. So what we can do is we can call it dp dt. The change in population over time is growing at a rate of 5% of the current population. So 0.05 p. 5% of the current population is the rate of change at which this population is growing. So our differential equation looks like this. Notice again that our dependent variable is the same as the variable we're using on the right. So we know we have an exponential function here. So if we were to solve this, we would have P equals CE to the 0.05 t based on the variables I used. But we're also told that the initial population is given by P sub 0. So when t equals 0, C will end up equaling P sub 0. So we can write this as P equals P sub 0 e to the 0.05 t. So this is a way that we can write a function for this particular population by starting with the differential equation and then solving. So remember, P sub 0 represents a number, right, which is the initial population, and our variables are P, which is our dependent variable, and T, which is our independent variable. Let's look at another example. Example 4. A bank account earns interest continuously at a rate of 7% of the current balance per year. Assume that the initial deposit is $5,000 and no other deposits or withdrawals are made. A. Write a differential equation satisfied by the balance in the account. So if we're talking about the balance, we could certainly write our differential equation as dB dt, which is how the balance changes over time. And we know that it's changing at a rate of 7%, which is 0.07 of the current balance, which is B. So the derivative, or the rate of change of the balance, is 7% of the balance. That's what our differential equation says. Notice that we haven't used the 5,000 yet, because the 5,000 impacts the solved differential equation and not the original differential equation. Part B wants us to solve the differential equation and sketch a graph of what that looks like. So if we solve this, we notice that again, dB is on the top and B is on the right, so we know it's exponential. So B equals CE to the 0.07 t based on the variables we used. Now we want to solve for C. So we know that the initial amount is $5,000. So the balance is $5,000 when time equals 0. So if we plug in a 0 here, this term is 1. Therefore, C is 5,000. So B equals 5,000 e to the 0.07 t. Now, if we were to sketch a graph of this, we'd be charting the balance over time. So we have to think about what that's going to look like based on our solved differential equation. Okay, so 5,000 is what we get when t equals 0. So that's where our graph starts. Now, because k is positive and c is positive, this is going to be exponential growth. So that's going to grow over time, like we saw in those graphs earlier. So our general idea is going to look like this. We're going to start at 5,000 and we're going to go up and we're going to grow exponentially over time. Let's look at another example. Example 5. The half-life of Advil in the human body is about 3 hours. What that means is that after 3 hours, only half of the original dose remains. Use the half-life to find constant K in the differential equation dQ over dt equals KQ, where Q represents the quantity of drug in the body T hours after it's administered. So we know by looking at this differential equation that this is going to represent exponential function. So the exponential function is going to be a function of Q, which is our dependent variable. So starting with part A, we have Q equals CE to the KT. So that's what we get when we solve this differential equation. But we want to use the half-life to determine our K. We can solve for K by using what we know about the half-life. The half-life is 3 hours. What that tells me is that when T equals 3, the amount of drug left in the body is half of the original amount. So that means I can write this as 1/2 of C, which is going to represent our original amount, equals CE to the K times 3. So notice that I don't know how much the original amount is. I don't know C. I don't know if it was 100 milligrams, 400 milligrams, but I can still solve this equation for K because I can divide C out of both sides, and then I'm left with 1/2 equals e to the k times 3. So if I take the natural log of both sides, I get natural log of 1/2 equals the natural log of k times 3. When you take the natural log of something with a power, the power will come down in front. So natural log of 1/2 equals k times 3 times the natural log of e. We know that the natural log of e is 1. So that tells me that k equals the natural log of 1/2 divided by 3. So now I've solved for my rate here. And what I want you to notice is that if you were to put this into your calculator and you were to do the natural log of 1/2 divided by 3, that's going to give you a negative number. So that means that k is negative. So this is a model of decay. And that makes sense because we're talking about how the drug leaves the body. Now, I'm going to leave my k as the natural log of 1/2 over 3 because that's an exact answer instead of rounding. So I want to keep it exact to reduce the amount of rounding error. So again, my k is the natural log of 1/2 divided by 3. Now for part B, now that I know my k, I want to know at what time will 10% of the original dose remain. So again, I go back to my original equation. I start here, Q equals CE, but now my k is the natural log of 1/2 over 3 times t. And I want to know when does half I want to know when does 10% of the original dose remain. So what I'm looking for is 0.10 times C, 10% of the original amount, which is our C, equals CE to the natural log of 1/2 over 3 t. So again, I can divide out the C's, and to solve for t, which will answer the question, what time, I'm going to start by taking the natural logs of both sides. So the natural log of 0.10 equals the natural log of e to the ln of 1/2 over 3 t. And again, if I take the natural log of something raised to a power, that something will come down in front. So I have the natural log of 0.10 equals the natural log of 1/2 over 3 t times the natural log of e. But the natural log of e is 1, which means that my t is going to equal the natural log of 0.10 divided by the natural log of 1/2 divided by 3. You can simplify this algebraically first, or you can plug this all carefully, very, very carefully, into your calculator. And we are going to calculate this one because we want to know roughly what time this happens. And if we don't put this into our calculator, I'm not sure we would have a good sense of what t this would be. So when we plug this in, we're going to get 9.97. So here, time was in hours. So that means that 10% of the original dose remains in the body when time equals 9.97 hours. So if we were to round this to the nearest hour, that would be 10. So 10% of the drug remains after 10 hours, which means 90% has decayed out of the body. So almost all of it is gone. So we're able to use what we know about differential equations paired with half-life to talk about some interesting things about how things are decaying out of the body.